People, today I want to talk to you about probability. And probability is simply estimates of how likely something is to happen. Probability will not tell us exactly whether something will happen or not. In other words, it can't tell us whether something will definitely happen or not. It will only give us that estimate, the likelihood. It will give us an idea of the likelihood. We live in a world of uncertainty and variation, heaps of variation. So statistical analysis collects and explores data to find a signal in all this noise. We want to find out some kind of structure beneath all this variation. We want to be more sure about the likelihood of something to happen or not. And it's often very useful if we can do it. Probability is the way of expressing uncertainty. In other words, we are not 100% sure whether it's going to rain tomorrow or not. So we express it as a probability, a certain percentage chance that it will rain tomorrow. And even insurance companies, they focus and work 100% on probability. What is the probability that you will make an accident? Because they want to make money, they want to be profitable, and therefore they put all the odds in their favor. You need to be able to identify the 4 different types of variation. We get natural variation, we get explainable variation, variation due to sampling, and it's also known as sampling error, and variation due to bad sampling, and this is known as non-sampling error. Remember, it's counterintuitive. Non-sampling error, it's very important, it's due to bad sampling. You know the story by now. Read through it and classify each of these statements as either true or false, and then resume the recording. The statement was, statement number 1, every Braeburn apple will weigh exactly 133 grams. People, this is false. We would not expect the apples to weigh exactly the same. I mean, even with your eyes, you can see that some are smaller than others. Number 2, statement number 2, if we buy 10 Braeburn apples from the supermarket, we expect the combined weight to be about 1,330 grams. People, this is true. You should be able to do that kind of calculations, but the important word is about. In other words, plus minus. Number 3, we would be surprised if the combined weight of 10 Braeburn apples is more than 2 kilograms. People, this is true. Apples do vary in weight, but all of them would need to be a lot heavier than usual for this to happen. Number 4, we would expect about half the apples to weigh more than 133 grams and a half to weigh less than 133 grams. People, this is also true. Natural products like apples tend to have a symmetric distribution, which means that about a half weigh more than the mean and half weigh less. Potential sources of error in estimating a population distribution using a sample. People, there's 2 kinds of errors, main types, sampling error and non-sampling error. If we talk about sampling error, it's not really that we've made a mistake with a sample. It's simply because the sample is not the whole population. In other words, if you've got a whole school full of children and you select 100 students from that school and you weigh them, you will never determine 100% the average weight of what all the students in the school would weigh. Okay? The best thing to do if you want that is to weigh all the children in the school, but Usually it's unpractical, and then you don't need the sample. Okay, so just take in mind, because of natural variation and so on, it's simply because the sample is not the whole population. So even if you take a certain sample and you take another sample, 100 students, you'll probably get different results. Not necessarily far removed, but different results. Non-sampling error, people, this is because of poor sampling methods, maybe a questionnaire or measurement error, and maybe because of behavioral effects. One cause of error can be when your sampling frame does not represent the population. In other words, you've got a sampling frame, but it does not represent the whole population. So ask yourself if any object in the population was equally likely to be chosen. If not, then there is a potential non-sampling error. For example, a self-selected survey. The statement is, because of natural variation, it is not wise to generalize from a sample of 1. Please pause and practice. People, this is true. If every item in a population were identical, we could know for a sample of 1 what all the items were like. In other words, just by looking at that 1, we can imagine, okay, this is how all the rest are. And here we can think, for example, of a sheep that's got 4 legs. So if you look at one sheep and you see the 4 legs, you can say, all of them's got 4 legs, and you will be correct. But when we look at the weight of sheep, of course, then you can never use 1 as a proper sample. One pair of size 8 jeans fits Emily perfectly, whereas another pair of size 8 jeans is a little tight. This is an example of natural variation. True or false? This is true. The manufacture of jeans is a process that will have a certain degree of variation in it. So it's reasonable to expect that even jeans of the same size will differ slightly. What about explainable variation? The statement is, explainable variation is variation due to known factors such as age, sex, and nationality. Pause, practice. This is true. Though we don't know exactly how much variation is caused by a known factor, we can use statistical methods to get some idea. Statement number 4, when we travel during peak time, the time taken to get home is always longer than when we travel at off-peak time. So this is always the case. So it is not an example of explainable variation. Is it true or false? Of course, this is false. This is a good example of explainable variation. If we collected all our travel times to work and compared those which were at peak time compared with those at off-peak, we would be able to get some indication of what variation is explained by peak, off-peak timing. The statement that I'm making, we can avoid sampling errors by taking a random sample. People, this is false. Sampling error is unavoidable. In all research, there's sampling error present, though a larger sample will help reduce the effect of the sampling error. The statement that I'm making, sampling error occurs because we are looking at the sample rather than a population. True or false? This is true, people, but if we could test an entire population, we would not have needed a sample. Okay, and we would not have any sampling error then. 2 students were each told to take a random sample of 10 students from the same class and find the average weight. They got exactly the same answer. This probably means They cheated and used the same sample. What do you say, true or false? This is true. It is unlikely that two random samples will give exactly the same mean. The phenomenon that there will be a difference between perfectly good samples is called sampling error or sampling variation. So remember, sampling variation or sampling error, that's basically the same thing. So don't think sampling error means there's a mistake. A sample is said to have a bias if all members of the population are equally likely to be selected. True or false? This is false, people, because the opposite is true. An unbiased sample is one in which all members of the population are equally likely to be sampled. Two students each took a sample of 10 students from the same class and found the average weight. They got different answers, so we can conclude that one of the samples must have been biased. This is false. They've got different answers because the samples were different, which they are supposed to be. So this is simply sampling variation. For random samples, we can also use the term random variable. In probability, when we talk about something occurring randomly, it means that we don't know ahead of time exactly what value it will take. We will usually have an idea of what values are possible and how likely each value is. For example, a ticket seller has some idea of the number of tickets they may sell on a certain day, including the minimum and maximum number and most likely number. But this model or set of rules is described as a probability distribution. When loading luggage onto airplanes, the weight of each bag can be represented as a random variable. We know the weight of the bag will be somewhere between 0 and 50 kgs. We can go further and say that if it was lighter than 7 kilograms, it would have been hand luggage. And the other limit at most airlines is 23 kgs. So we do not expect it to go over 23 kilograms either. Inferential statistics use information from a random sample to draw conclusions about the populations from which it was drawn. So, for example, we might randomly choose 10 bags from the conveyor belt, weigh them, and get an idea of how heavy all the bags are. Simulation is a technique for imitating the behavior of a situation that involves elements of chance. So the simulation uses physical tools, and here we can think of things like coins and dice and random numbers generated by a calculator or a computer, and random number tables. The purpose of a simulation is to find out information about complex events that involve uncertainty. We've already discussed it in economics as well, but simulations can be used to help us to understand the principles of inference. To come back to probability, it's a way of giving a number to express how likely something is to happen. So the value 1 is assigned to something that is certain, while 0 is assigned to something that definitely won't happen. So all this in-between values closer to 0 are less likely to happen, and those closer to 1 are more likely to happen. Often probabilities are expressed as percentages. For any given circumstance, called a trial, the probabilities for all possible outcomes must always add up to 1. Remember that. We can often say, there's a 10% chance of this happening. I'm 90% sure, but it's just subjective. So I want you to go to the following link, this probabilitysurvey.com, and go and test your estimates or your perceptions with that of the rest of the world. In this table over here, we've given a decimal for P, and P is all about the probability to pass. If the probability is 1, we can also express it as 100%. In other words, it means I will definitely pass my driver's license on my first attempt. And over here on the right hand side is the diagram. So the probability of passing is represented in blue. When it is 0.95 or 95%, it's very likely that I will pass my driver's license on my first attempt. And there you can look at the scales and you will see when it's 0, there's no blue on it. So I will not pass my driver's license on my first attempt. That's for sure. So probabilities are simply used to communicate how likely something is, or how likely it is for something to happen. They're also used in mathematical models, and the mathematical model that includes uncertainty is called a probabilistic model or a stochastic model. I like to use stochastic models when trading. Exact, a priori, and traditional. Sometimes we can make a good model or an estimate of what the probabilities are for a given situation. If we know that certain things are equally likely, we can use that equally likely property to calculate probabilities that combinations of those outcomes will occur. And we call this exact probabilities, or a priori probabilities, or traditional probabilities. But for the sake of this course, we're just going to talk about model estimates. So take note that the equally likely refers to the outcome event to be just as likely as for any of the other events to happen. And that's important to know. Experimental frequency or historic data. Other times we can't use the equally likely property, as the events are clearly or possibly not equally likely. So often we really don't know how likely something is. In this case, we can either set up an experiment and collect data, or we can use historic data. The relative frequencies of the events provide an estimate of the probability of that event happening in the future. But the problem with this method is that we need many instances to get a good picture of what's going on. And the problem is that we are assuming that the past is a good predictor of what will happen in the future. And this may not necessarily be the case, for example, after a policy change. A model built on previous or experimental data is called an experimental probability model or an experimental distribution. To come back to the policy change, where I've told you that the past data can be a good predictor of the future, unless something changes. You will often see it in commodity markets. When you are trading commodities, you can use past data and you kind of like expect that similar things will happen again. What is subjective probability? We've already mentioned it. So sometimes we can't collect data because the event we're trying to assign a probability to has never happened before. Any number we assign is based on intuition and human judgment. And this is called a subjective probability estimate. Often a subjective estimate is the best that we can do. It's a form of a model, but it's probably not the best model there is. It's interesting that there's always like a long run pattern when it comes to data. One interpretation of probability is that it predicts how often something would happen if we could repeat the same trial over and over a very large number of times. In other words, then eventually, based on the results that we've got, we can with relative surety predict the future. So a netball team of 7 draws a team member's name out of a bag each week to provide oranges for halftime. The name is put back ready for the following week, and we would expect over a long time that each team member would provide oranges about the same number of times. However, it may take a very long time before the numbers will even out. In other words, in the short run, we will usually get something that people will describe as unfair, even though it was randomly chosen. For large numbers of simultaneous trials, we can use probability to work out proportions. Let's say there is a 15% chance that any ewe female sheep will give birth to triplets rather than twins or singles. We can use this probability of 0.15, multiply it with 1,000, and then we will see, okay, 150 ewes in this herd of 1,000 will give birth to triplets next season. Okay, so once we also know the probability of the twins and the singles, we can use this to estimate the total number of lambs. So this is because I've told you the different probabilities will always add up to 1. There's actually a law of large numbers. There is a probability theory called the law of large numbers, and this law involves performing the same experiment a large number of times. And according to the law of large numbers, the more trials you make, the closer the distribution will be to the theoretical distribution. The thing is, though, it needs to be a really large number. For example, say we're interested in seeing the probability distribution of the times taken to run a marathon. We can't measure the times of 10 people and expect that to be a good indication of the distribution of times. But however, if we took the times of several thousand people, that should give us a good model of the distribution. In the previous section, we had an example of this netball team. And it is true that some of the players might get upset and they might feel that it's unfair if one player's name is drawn more than the rest of the players. So let's say we use a computer to simulate drawing a name 28 times. With 7 players, we would expect each name to be drawn about 4 times. So, but instead, we get something like this. Number of times chosen: Anne 3, Beatrice 7, Carol 4, Dindy 4, Ella 5, Fia 2, Harriata 3. Can you see the proportion of times? We expect it to be 0.14, but look at the variation. This was drawn by a random process. And one girl, Beatrice, was chosen 7 times. This is a proportion of 0.25 compared with a theoretical proportion of 0.14 or 1/7. If we use the same thing again, but this time we use the computer to draw a name 2,800 times, note that the proportions have been rounded to 2 decimal places. In other words, it's now very near to what we've expected due to the large numbers. Remember this, we will come back to this and you will see why it's important. You can see that there's a more even spread when we do a large number of trials. This phenomenon is due to the law of large numbers. Now that you know what probability is, we're going to continue to estimating probability. So the probability of A is the number of ways that A can happen over the number of possible outcomes. Rina has been shopping and visited 5 different shops. When she got on the bus, she found that she dropped a bus pass somewhere. What is the probability that she dropped a bus pass in one of the shoe shops? There are 5 shops, but 2 of them are shoe shops. So the probability for the bus pass in the shoe store is the number of ways that A can happen over the number of possible outcomes. It's important to realize that we're making assumptions here. We assume that the bus pass would be equally likely to be in each one of the shops and not anywhere else. So we made certain assumptions that the bus pass can only be in one of the shops and not anywhere else. And these assumptions may be or may not be reasonable. The number of ways this outcome could happen is 2. There are 2 shoe shops. So the probability to find the bus pass in the shoe store is the 2 shoe stores that exist out of the total number of possible shops. Where do we get this from? The number of possible outcomes is 5 because Rina visited 5 shops. So the probability is 2 divided by 5, and it can be written like this. It will give you 0.4. That's a probability of finding it in those 2 shoe stores, or the probability of finding it in the shoe stores are 40%. It is only after assuming that the bus pass is equally likely to be in each of the shops and that it won't be anywhere else that we can say that the probability that the bus pass is in the shoe shop is 2 out of 5, or 0.4, or expressed as a percentage, 40%. So if you are given a calculation like the mentioned as a mathematical exercise, you can usually assume equal likelihood. In other words, the possibility is equally likely to find it in any one of those 5 shops. Remember, we've said the probability to find the bus pass in the shoe shop is 0.4 or 40% because of the fact that there's 2 shops. However, be aware of the assumptions that you are making. If you are using dice, coins, or balls and urns, it is usual to assume an equal likelihood. Okay, now for $1 million question. You have a class, and in that class there's both boys and girls. So what is the likelihood or the chance of selecting a girl? Give it to me percentage-wise. So please stop the recording and first do that. People, this is what they call like a bad example. And you should be warned, if you've said like 50%, you've made a real big mistake. Because sometimes it will be totally wrong to assume equal likelihood. The possible outcomes of the chance happening or the trial need to be equally likely for this approach to work. Here is an example of how some people can get it wrong. We have a group of boys and girls, and one person is selected at random to be the spokesperson. Because there are 2 different outcomes, namely boy and girl, you can think that the probability of picking a girl is half. But this assumption is wrong. It's only if there were equal amounts of boys and girls in the group that it will be true. In other words, 10 in the group, in other words, 5 must be boys and 5 must be girls, then it would have been true. Because it would have been 5, the number of ways that it can be, divided by 10, the number of possible outcomes. So this is how you're going to calculate it. There you can see the number of girls So that's a number of ways that it can be, and this at the bottom is the total number of possible outcomes. So if there's 5 girls, 5 boys, then it will be 1 out of 2. With 7 girls, there could have been 7 equally likely ways that a girl could be picked out of the 10 possible outcomes. So a mistake can be made by assuming that the 2 likely outcomes are boy versus girl, when in fact there were 10 equally likely outcomes corresponding to the 10 group members. And this is a common mistake that people make. Going back to Rina's example, where we calculated that the likelihood for the best bars to be in the shop can be 2 divided by 5 is 0.4 equals 40%. People, that's actually just part of it. It's not the final answer. Because the probability that it could be at the jewelers is only 1 divided by 5, 0.2, 20%. In other words, we were only talking about one shoe shop and not both. We got 3 separate outcomes that's basically making up what we call the sample space or the list of all the possible outcomes. Basically, it was a shoe shop, the dress shop, and then the jewelry shop. So the probability must add up to 1, like we've said, because we define them as all the possible outcomes. So the sample space is simply all the possible outcomes. And then, just to repeat myself, another way to estimate the probability is by using historical data or running an experiment. This is known as an experimental estimate, probability from data, or a relative frequency. We assume that the future behavior will be similar to historic behavior. We use the following formula: the number of times A occurred over the total number of observations, and that's giving us the probability of A. Let's look at this example where you've planted 100 seeds and found that only 73 of them germinate. Then you can look at the probability of germination, and it's simply the number of seeds that germinated over the total number of seeds that you planted. Now that we know that 73 out of that 100 seed germinated, now we can look at the proportion. And people, this is really not difficult. Say, for example, if you buy 100 eggs and you're using 25 of those eggs, at the end of the week, the proportion that you've used, 25 divided by 100, is a quarter. In other words, 25% of the eggs. And this is exactly how it works. 73 out of 100 seeds germinated, so we can say that the proportion was 73%. People, I don't like the way that people make it difficult to distinguish between proportion and probability. Proportion is just something that already happened. So you can see it's scientific, it's empirical. In other words, you can see this is how much I've used. A probability is, if you use 25 eggs a week, so the probability that you will use a quarter of the eggs in next week, that's what the probability is, you know. So probability is basically based on the future. So if you can just remember it like that. So probability is a measure of uncertainty, whereas proportion is a measure of certainty. And the difference is not in the calculation, but simply in the purpose to which the metric is put. So over here you can see the description. Probability represents the chances of some event happening. What's the chances? But proportion summarizes how frequently some event actually happened, past tense. Okay, the type of value for probability, it's a theoretical value. It's a good guess. It's a scientific-based guess. And then proportion, people, that's empirical. So people, remember, we got 73% of seed that germinated. It's important that you use as many trials as possible, because if you use a too small number of trials, then the data will be of such poor quality that you can never base or build an accurate model based on that data. And you can see it over here for yourself. Over here, we've taken 2 seeds and planted it to look at the germination proportion, the proportion of seed that will germinate, or so that we can use it in future for probability estimation. And there we can see we've planted 2. 1 did not germinate, 1 did germinate. So we can say 50% of the seed germinated. People, compare the 50%, this answer, to the 73% that you got, and you will see this is definitely not accurate. People, if we have no model or no experimental data, no historic data, in these kind of situations, we can just use our prior experience or even a guess. But the problem is these subjective probabilities are really not good estimates in general. The model that we're going to follow in order to determine probability is simply the following formula. The probability of a certain outcome, usually we will just say P in brackets outcome, is the number of ways this outcome can happen over the total number of possible outcomes. The only reason why we say can, because it did not happen yet. But the formula is very simple. To make it easy for yourself, just think like a teacher marking some examination papers. And then 10% of the students fail. So basically 90% passed. So you can just think about that proportion. You know, we've calculated that 90 out of the possible 100 made it. You know, so that's historic. But you can use exactly the same thing to determine probability. Exactly the same formula. How many students are likely to pass? People, then it will be 90 over 100 to give us the probability. Exactly the same thing. People, now I want you to pause the recording and please do the calculation that I've highlighted for you in blue. In other words, the blue highlighted portion only. Claire is concerned about her potential opponents in an arm wrestling competition. 15 other people are competing. 6 of them she has defeated before. 4 of them have beaten her, and the other 5 are an unknown quantity. Claire wants to know the probability that her first opponent will be someone she has defeated before. Okay, that's what I want you to calculate. What is the probability that her first opponent will be someone that she has defeated before? So please calculate that probability. And there's some hints that I've given you to follow. In this example, one trial is one selection of an opponent. There are 3 different outcomes. Someone she has defeated, so that will just be P in brackets D. In other words, the probability of D. That's what you should determine now. And then someone who has beaten her, B. Don't worry about that yet. And someone unknown, U. People, the probability of unknown. U for unknown. You don't have to determine it now. These 3 outcomes are the only outcomes possible. So their probabilities must add up to 1 in the end. That's a way that you can test yourself to be sure that you've done it correct. So what is the probability that her first opponent will be somebody that she defeated before. So the probability of D, of somebody that she defeated before, you will take the number of opponents that Claire has defeated before and put it over the number of possible opponents. Okay, so the number of opponents Claire has defeated before divided by the number of possible opponents. Just look at my blue arrows. So the number of opponents Claire has defeated before, we know it's 6, and we know the number of possible opponents is 15. So people, there is a 0.4 possibility that or probability that she will get somebody that she has defeated before as a first opponent. Now I want you to think about what you've done and calculate the probability of someone who has beaten her before. And only then you go over to the next slide. If you want some of the information, you can always go a little bit back, and from there you can go forward again to mark your calculations. So people, the probability of B, B standing for beaten, somebody has beaten Claire in the past. So you look at the number of opponents who have beaten Claire, and you see it's 4. And now you just put it over the number of possible opponents, and there's your probability. So it's like a teacher marking exam papers, like I've told you. If there's a possibility that you can get 100 marks, 100%, but if you only get 10, then I take the 10, that's what you can achieve is like 100, but you only achieve 10, and now I put it over the number of possible marks. So it will be 10 out of 100. That will be the ratio or the percentage that you've earned. So we do exactly the same over here. And 4 over 15, if you do the calculation, you will get a probability of 0.267. The probability to face somebody who has beaten Claire before is 0.267. Okay, people. And if you want to express it as a percentage, you can just multiply it with 100. 27% basically. So now calculate the probability that the person will be unknown. People, the last calculation that you must do is to find the probability of U. U is standing for unknown, so it's P in brackets U, is basically the number of unknown opponents. People, it's easy to see there's only 5 left. So 5 over 15, and immediately you can see it's supposed to be a third. So your answer is 0.333. You don't even have to use a calculator. Okay? So that's it. That's your answer for the last one. But now you can test yourself. In other words, the first thing highlighted in blue that you calculated, what was the possibility that the first opponent would be somebody that she defeated? And that probability was 0.4. And what was the probability of getting somebody that defeated her? Or what will be the probability of getting somebody that defeated her in the past? Okay, that probability is 0.267. And then the last one, what is the probability of getting an unknown opponent? People, that will be 0.33. Okay, so if you add it, you will see, it's giving me 1. And now you must know, yes, I couldn't have made a mistake. And if they ask you to express it as a percentage, people, then of course the 0.4 will be 40%. The 0.26, you just multiply it with 100 in each case, will be 26.7%. And the last one, 33.3%. And if you add it all, you will get your 100%. Okay, if you're supposed to express it as a percentage. So these 3 outcomes make up the whole probability distribution and add up to 1. You're trying to work out how many ice cream cakes to order for your ice cream shop. To work out how likely you are to run out, we look at the records of weekly sales for the past 20 weeks. And I taught you that we always use historical proportions that we've determined. You know how to determine a proportion. I told you it's almost the same as a probability. It's just something that already happened, so it's actually easier. So we use historic proportional data to determine future probabilities. The sales each week are 2, 2, 2, 2, 0. Okay, so there was 1 week, it was probably very cold and nobody wanted to eat ice cream cakes. And then if you continue with the data later on, you will see there's another time where there was 0 sales and a third time where it happened. So basically what I've done, over this 20-week period, I've looked at all the sales per week. So for 0, how many times did it happen? The frequency was, in other words, how many times out in that 20-week period? People, 3 times. Okay, we only got 1 ice cream cake sold. How many times did that happen over this 20-week period? 2 times. And this is basically how you read the table. So basically I want you to look at this table, and now I'm asking you to do a calculation on the next slide. Okay, people, so here's the work that you must do. Work out the relative frequency for each of the weekly sales as an estimate of the probability for future weeks. We do this, in other words, how are you going to get the relative frequency? If you've already forgot, because we already did it, we do this by dividing each frequency by the total number of weeks. In this case, it is 20. So at the end of the day, you will get a probability, and remember to add the probability numbers. Okay, the reason why you should add the probability numbers, I've not left any space for it. It's just to test yourself to make sure that you've worked accurate. So people, your completed table should look like this. If it's not looking like this, make sure, go back and make sure that you can do these calculations and that you do understand what's going on. Okay, so I've got a few questions for you. Using the stuff that you basically worked out, your table, tell me what the probability is for 5 ice cream cakes. And then what the probability is for 0 sales of ice cream cakes. And what the probability is for selling 3 cakes per week. Okay, people, so the first one, use your table and tell me what the probability is of 5 ice cream cakes. People, that was a tricky question. It's 0 because you've already seen that if you add all the probabilities, you will get 1 or 100% of your data. So you can't bring in extra or something from the outside. It's impossible. Okay, what the probability is of 0 sales of ice cream cakes. Okay, people, you just read it off because you've seen if you add all these probabilities, you're getting 1. So you know it's correct. So your probability for selling 1 ice cream or 0 ice cream cakes is 0.15. And what is the probability of selling 3? Okay, people, you just read it from your table and it will be 0.25. And the reason again why you know this is because you've tested yourself. So I'm just going to ask you a few questions. You must pause each time after going to the before going to the next slide, where you will find the answer. Otherwise, this revision, honestly, then it's got no purpose. Please, people, you have to do it in order for your brain to kind of like tell you whether you know this stuff or not. And if you can't answer it and you think about it, people, then your brain will give you your subconscious mind the information, or the message that the information is really important. What type of estimate is this? There are 10 bottles of ginger beer in the fridge. 4 of them are diet. The probability of grabbing a diet ginger beer without looking at what you are about to grab is 0.4. What type of estimate is this? Okay, people, it was a model estimate, and it's because we have information about equally likely outcomes, and that's the 10 bottles from which to create a model. What type of estimate is this? Out of the last 20 job offers made, 5 people have not taken the job. From this, the human resources manager decides there is a quarter chance that an offer will be turned down. People, this is an experimental estimate, and simply because the human resources manager is drawing on historic data to estimate a probability. What type of estimate is this? After a particularly happy day, Fred thinks his chance of buying a winning scratch and win ticket is about 10%. What kind of estimate is this? People, this is a subjective estimate because he's just going with his feelings. What type of estimate is this? Based on a sample survey, we say that the probability that the person can identify the toothpaste brand from the advertising slogan is 0.85. People, this is an experimental estimate because it's drawing on experimental data. What type of estimate is this? Jay estimates that there is a 5% chance that he will be invited to give a keynote address in the next 2 years. People, if I have no data to draw on, I will just basically make an educated guess. So it's a subjective estimate. So what type of estimate is this? Television advertising is assigned 20% of the airtime in prime time. The probability of turning on the television at prime time and seeing an advertisement is 20%. People, it's a model estimate. The proportion of time is known, so this is a model estimate. I'm just thinking that the slides are maybe becoming too long, so in order to keep it like under an hour, I'm going to stop now, but I will send you the rest.